Hey, I have a question before we get started.
What's up, Carrie?
Will you be posting this video today? Because I'm in Arkansas and we're under a tornado warning, so I don't know how long I'm gonna have power.
Yes, I will do it. Yes, I
Okay,
will do it today.
awesome, thank you.
You're getting a sticky note so that I don't.
Okay, thanks.
Yeah. I'll try and do it just right after this. Post video ASAP. Okay. So you will all have your fourth test this weekend. Well, starting this weekend, right? That's Sunday, Monday. It'll cover gases, solutions, and then acids and bases. We've got some more in acids and bases that I want to go over. So let's see here. Okay. So we did solution stoichiometry last time. Good with that. So I want to talk about the difference between a strong acid and a weak acid. When somebody says, oh, it's a strong acid, or oh, it's a weak acid, it doesn't have to do with the concentration of the acid. So it's not like a strong acid is, like more than 6 molar or something like that, arbitrary. It has to do with the dissociation or the ionization of the acid itself. So hydrochloric acid is an example of a strong acid. What it means is that it completely dissociates in solution. So every hydrogen and every chlorine will break apart to form ions. So you get a lot of H pluses per molecule. You get 1 H plus per molecule. A weak acid, an example of that would be HF, is one that doesn't completely ionize in solution. So that means that some of the HFs will break apart into their ions and some of the HFs will stay paired as a molecule. So you don't get quite as many ions floating around in solution. One way that you can identify it, if you're looking at like an equation like this, it'll have a single arrow. So you can see the hydrochloric acid, you drop it in water and every hydrogen will bond with the water to make that hydronium, right? So that's our acidic thing, and the chlorine will be floating around. So everyone breaks apart. In a weak acid, and as far as this being electrolyte solution, pure water, I swear I can speak today. Pure water is not a good conductor of electricity because it doesn't have a lot of ions in it. But if you put hydrochloric acid in solution, there's all these charged particles floating around. So the water can act as a current bridge for, let's say, like a light bulb that's plugged in. You can run a current through it. You can electrocute yourself in a electrolyte solution, but not in a pure water solution. Now, here's a list of the 6 strong acids. As far as how this goes, there are 6 strong acids. Any other acid is classified as a weak acid. So if you know these 6 strong ones, you will know all the weak ones because it just won't be one of these. 4 of them, or rather 5 of them, are monoprotic acids, meaning that they contain only one ionizable proton. So hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, perchloric acid, and then we have one diprotic acid, which is an acid that has 2 hydrogens that can be ionized, sulfuric acid. But remember, each hydrogen will ionize on its own. Okay, so we would ionize the first hydrogen, and then we would ionize the second one at a later point. A weak acid, one way that you can sort of identify that, at least if you're looking at an equation, that it's a weak acid is, do you see the double arrow here? That means that some of the HF is breaking apart and some of it is recombining back into the molecular form. So what you will find in solution is that you have HFs, the original molecule. You'll have a certain concentration of that, and then you will have a small concentration of the hydronium ion, which gives it the acidic quality, and those fluorines floating around. This situation is a much weaker conductor of electricity. Why? Because you just don't have as many ions floating around, right? Because some of the molecules are staying as whole, this molecule has a neutral charge. So we'll have a weaker light bulb current. Here are weak acids. Here's some tables of weak acids. There are way more than this as far as how many weak acids there are. I think with strong acid bases, if you know the 6 strong ones, just assume all the other ones are weak. When trying to calculate the H3O plus concentration in an acid, if you have a strong acid like this, whatever the concentration is of the molecule will equal the concentration of the H3O plus, because every single one of these breaks apart, correct? If it's a strong acid, every one will break apart into a hydrogen and a chlorine. So if I have a 1.5 molar HCl solution, I also have a 1.5 molar H solution, or H is the same thing as this. Remember, those two things can be interchangeable because it completely dissociates. So since HCl is a strong acid, it completely ionizes. You will have equal concentrations. Whatever the molecule's concentration is also going to be whatever the H concentration is, or the H3O plus concentration. What about this thing here? Do you see this guy? This is a weak acid. So when it's a weak acid, it means that not all of the hydrogen will ionize from the molecule. Some of it will stay combined. So if the overall concentration of the molecule is 3 molar, what is the concentration of the hydrogen? Well, this isn't like an exact science. It's just something less than 3, right? So since it's a weak acid, we get partial ionization. If we want to calculate the H3O plus concentration, it's just going to be something less than whatever the original concentration of the compound is. There's not going to be any sort of like math for that. This is really the important thing, is that if it's a strong acid, you can assume that whatever the concentration of the molecule is also the concentration of the acidic thing. What about this last one here? This last guy? Is that a strong acid? Oh yeah, that's a strong acid. So we would assume that the hydrogen concentration, again, or the H3O plus concentration, is going to be equal, because every H and every NO3 breaks apart. So they would have equal concentrations. Good with that conceptually? If it's a strong acid, equal concentration. Okay, if it's a weak acid, it'll be something less than whatever your molecular concentration is. Okay, we're going to keep moving from there. So a strong base, just like a strong acid, is something that completely dissociates in solution. Here's a list of strong bases. They're really anything that is in column 1 or column 2 combined with hydroxide. Unlike diprotic acids, where they OH or the H is ionized separately, here it ionizes all at once. So if barium hydroxide goes into solution, you're going to get 2 of these for every 1 molecule. So NaOH, there we go. We throw it in solution, and every sodium and every OH breaks apart. This OH, again, is what is giving you the basic qualities of solution. A weak base is analogous to a weak acid, unlike a strong base that contains OH and dissociates in water. The most common weak base will produce OH by stealing a hydrogen from the water or accepting a proton. So we've got some sort of weak base. It's going to snag one of those hydrogens, and that's where you're going to get the OH production. But this is moving in both directions, so we do have some of the original weak base as well. If you're wondering what is B, this is just a generic term for whatever the weak base happens to be. So NH3 is a good example of a weak base. When we throw that thing into solution, some of the NH3s are going to steal a hydrogen and become NH4 plus and leave the OH. Some of them are just going to stay NH3. So we don't have quite as much OH floating around in solution as we would if we were dealing with this guy, where like we get a lot of OHs. There are a lot of weak bases. Yeah. Okay. So looking at this, I want you to determine the concentration of the OH for each of these things. I will tell you right now, we want to do OH. This is a strong. This is a weak. This is a strong. But remember, in this last one here, you get 2. Okay, 2 OHs for every molecule. So just take that into account. I'll give you just a minute to calculate that out, or just sort of generally get an idea of what it is. Okay, so for this one, the first one is a strong base. It has a concentration of 2.25 molar, so we would assume that it's going to completely dissociate. The OH concentration should also be 2.25. Right? This here is a weak base. The base itself is 0.35 molar. Because it's a weak base, we know that our OH concentration needs to be something less than the original concentration, so less than 0.35. This last one here, this is a strong base, but this one's a little bit different than situation A because here you're getting an OH, but you're actually getting 2 OHs. So your concentration should be double whatever your molecular concentration is. If this is 0.025, when this thing breaks apart, this one molecule breaks apart, you actually get 2 OHs. So we multiply it by 2 and get 0.050 molar. You don't do that with acids though, because acids, the hydrogen pulls off one at a time. Bases like this, they pull off together. All right, so we're gonna move into some calculations here. We talked about this idea of water as being amphoteric, meaning it can be either an acid or a base. Even if you have a sample of 100% pure water, there's nothing else in it, the water will ionize with itself. I don't know why. Here, water is acting as a base. So water will ionize with itself, meaning it does this. I don't even have the equation on here. So in a sample of pure water, I'll have water plus a water. And one of these waters will give up a hydrogen and the other water will accept it. So we end up with H3O plus and OH minus. You'll get a small concentration of each of these. Put a double arrow because this is coming apart and recombining. So what is that concentration? Well, it's a specific amount at 25 degrees Celsius. The constant, and because anytime one water transfers to another water, it means that the concentration of the H3O plus and the OH would be equal to each other, right? Because it takes 2 regular waters, one transfers to the other. So at pure water, you've got the H3O plus concentration will be equal to the OH concentration, and this is what it is, 1.0 times 10 to the negative 7 molarity. concentrations that we're going to be talking about in the next like 15, 20 slides are all going to be in molarity, moles per liter. So we can do this nifty thing where we take the concentration of each of those and we multiply them together. We get the ion product constant, which is known as the Kw constant. If I take 1.0 times 10 to the negative 7th and I multiply it by 1.0 times 10 to the negative 7th, this concentration times this concentration, I get this thing right here. 1.0 times 10 to the negative 14. This is the Kw constant. And this is in fact true for any equation or any solution. So the amount of H3O plus in solution times the amount of OH minus in solution will always equal 1.0 times 10 to the negative 14. That's not just for water, that's for hydrochloric acid, it's for sodium hydroxide. Anytime you have a solution, you can find this concentration times this concentration will always equal this. And we'll do some calculations. If we're in a neutral solution, these two things would equal each other, right? The amount of acid would equal the amount of base, making it neutral. So yeah, it doesn't even give us the equation. So we're gonna do this. So we know that H3O plus concentration times the OH minus concentration is equal to 1.0 times 10 to the negative 14. Always the case. So if I know the H3O plus concentration, like look at A here, the H3O plus concentration is 7.5 times 10 to the negative 5th. I can calculate the OH concentration because we just plug it in, 7.5 times 10 to the negative 5th times OH will always equal 1.0 times 10 to the negative 14. If I want this, I just divide both sides by 7.5 times 10 to the negative 5th, 7.5 times 10 to the negative 5th. So we take our 1.0 times 10 to the negative 14 and divide it by the 7.5 times 10 to the negative 5th. I want you to plug that into your calculator because I want you to be good, happy, comfortable with exponents divided by exponents. So our OH concentration is 1.0 times 10 to the negative 14, and that ends up being divided by 7.5 times 10 to the 5th, and we get 1.0 or 1.3 times 10 to the negative 10th. Okay. If you didn't get 1.3 times 10 to the negative 10th, if your exponent was off, make sure you're putting this in parentheses or use the EE button. So then it says the first part is to calculate the OH concentration. The second part is to determine whether it's acidic, basic, or neutral. So what is the concentration again of the H3O plus here? The concentration of the H3O plus is 7.5 times 10 to the negative 5th. The concentration of the OH is 1.3 times 10 to the negative 10th. Which number is bigger? This number here or this number here? Well, the acidic thing is bigger, right? This is only 10 to the negative 5th. This is 10 to the negative 10th. So 10 to the negative 5th is bigger. It means you have more acid in solution. It means your solution is acidic. I want you to do B and I want you to do C. Okay, so I want you to figure out the OH concentration if your H3O plus is 1.5 times 10 to the negative 9th. I want you to tell me if it's acidic, basic, or neutral. And then I want you to do the same thing for 1.0 times 10 to the negative 7th. You'll use the same equation. So the setup is really identical to this A part. You're just going to change out that denominator. So instead of 7.5, you'll put that 1.5 times 10 to the negative 9th. So I'll give you 2 minutes for that. All right, so for the second one, we are going to substitute the denominator for that 1.5 times 10 to the negative 9th, and we should get an OH concentration of 6.7 times 10 to the negative 6th. Okay, so what was our original H3O plus concentration? The H3O plus concentration was 1.5 times 10 to the negative 9th. The OH is 6.7 times 10 to the negative 6. Which number is bigger? The basic component is bigger, so the solution will then be basic, because you have to think about like the acid and the base are going to be sort of neutralizing each other. So if there's more base, there's not enough acid here to neutralize all that base, and we end up with a basic solution. The last one, C, when you plug it into the equation, you should get an OH concentration of 1.0 times 10 to the negative 7th. What's happening here? Well, in this situation, your acid is equal to your base concentration, right? That becomes a neutral solution. You could do this exact same thing, and I could give you the OH concentration, and you would have to calculate the H3O plus concentration, okay? It's the same system, because here's the equation. So it always equals this. You'll be given one or the other to solve for the other one. So I'm going to put this equation into, here's that information. I'm going to put it into this square that I think is helpful for people. So make a square, and in the upper left-hand corner, write the word pH. Actually, no, not pH, sorry. Write H3O plus concentration. H3O plus concentration. Again, that's talking about an acidic thing. In the upper right-hand corner, put OH minus concentration. Below the H3O plus, put pH. And below the OH, put POH. So we can go back and forth between the concentration of H3O plus and OH using that KW constant, because, like we said, H3O plus times the OH concentration will always equal 1.0 times 10 to the negative 14. So if you're given this, you can solve for this. If you're given this, you can solve for this. We're going to look on the vertical limbs here next. So how does pH relate to H3O plus, or the concentration of the acid? pH. The H is talking about the hydroxide or the hydronium. So how much hydronium or how much hydrogen do you have floating around in solution? The more hydrogen you have floating around in solution, the lower your pH will be. So let's look at pH here. So hopefully you're kind of familiar with the pH scale. It's a scale of 0 to 14. You can have negative pHs, but we're not going to get into that. But 0 to 14, neutral pH is 7, right? That's like pure water. As the numbers go down, you become more acidic. Okay, so weak acids or weakly acidic are 6, 5, 4s. Strong acids are like 2s and 1s. Bases, weak bases are 8, 9, 10. Strong bases are 12, 13, 14. These things balance each other out. So if you have something that's strongly acidic, you need something that's strongly basic to bring it back to that neutral pH of 7. pH is it's a logarithmic scale or an exponential scale. So a decrease of 1 unit on the pH scale corresponds to an increase in H3O plus concentration by a factor of 10. So if I'm going from a pH of 4 to a pH of 3, I'm increasing how much hydronium I have by a factor of 10. If I go from a pH of 3 to a pH of 2, I've increased by another factor of 10, or I've increased by a concentration of 100 from pH of 4. So it's not like an incremental scale. Going from pH of 4 to 3 is not the same thing as going from 3 to 2, right? It gets exponentially bigger. So because of that exponential stuff, it doesn't even, they don't give, these slides are horrible right now. I don't know what's going on. They're not giving us anything. So we need the logarithmic relationship. So the relationship here, so if we have this and we want to solve for this. So pH equals the negative log of the H3O plus concentration. So it's a logarithmic scale. As this number goes up by a factor of 10, this number will go down by a factor of 1. If you're wondering what is log, log is a button on your calculator. Think of log as the opposite of exponent, or 10 to the. So like multiplication and division are opposite of each other. Addition and subtraction are opposite of each other. Log is the opposite of 10 to the. So if I want to go the other way on this scale, let's say I have pH and I want to figure out H3O plus, the H3O plus concentration is equal to 10 to the negative pH. So log here is the opposite of this thing here, 10 to the pH power. All right, so we've got those equations written down. This is also true for something called pOH. You guys, probably aren't as comfortable with pOH. pOH measures the OH concentration as opposed to the H3O plus concentration. The equations are very similar, except instead of putting H3O plus concentration, we put OH concentration. So if I know my OH concentration, pOH is going to be equal to the negative log of the OH concentration. I want to go the other way, and I know the OH concentration. Or I want to find the OH concentration. OH concentration equals 10 to the negative pOH. So y'all seeing how these equations are like mirrors of each other, but this one on this side is talking about the acid stuff. This over here is talking about the base stuff. And while we're at it, let's just complete the square. How do we get from pH to pOH? Well, that's like the simplest equation. pH plus pOH always equals 14. There's no way to crisscross, okay? If I gave you the OH concentration and I wanted you to find pH, you would have to go through a two-step problem. I probably wouldn't go this way though. I would go this way because this equation is so fast and easy, right? If you figure out your pOH, you can real easy figure pH. You just subtract it from 14. Let's do some practice with some of these equations though. I just wanted to make sure you had it all written out. So, all right, first one here. We've got an H3O plus concentration of 1.8 times 10 to the negative 4. I want to know what the pH is. Okay, so I want you to use the equation for this one. pH equals the negative log of the H3O plus concentration. I want you to go ahead and plug that in, tell me what the pH is, and then decide if it's acidic, if it's basic, or I guess if it's neutral. In this case, it's going to be acidic or basic. When using your phone calculator, well, not that anybody is using their cell phone as a calculator, but if you are, you have to plug for, because I have at least for my iPhone, you have to plug in the number first. Like, so I would plug in 1.8 EE -4. I have to plug that number in first, and then I hit the log button. Okay. If you have a more, if you have an actual calculator with parentheses and stuff, you'll put the log button in first and then put the digit that you're trying to compute. Don't forget the negative either. If you don't put the negative in, it will not work itself out. So I want you to plug this into your calculator. I'll give you 20 seconds. Okay, so looking at this first one, we'll plug it into that equation where pH equals the negative log of the H3O plus concentration. You plug the 1.8 times 10 to the -4 into the equation. Again, depending on your calculator, you may plug this in after you hit the log button, or you may plug it in before you hit the log button. There is a negative in front of here, which will flip the sign, because the log of 1.8 times 10 to the -4 is -3.74. The negative gets flipped and we end up with a number of 3.74 for our pH. Now, is that acidic or basic? Low numbers mean it's acidic, right? Anything less than 7 is acidic. Do the second one here. You're given an H3O plus concentration of 7.2 times 10 to the -9. It's the same equation, so just plug it in. I'll give you 30 seconds. Okay, so plugging this in, you should get a pH of 8.14, which is basic. You might start to see with these numbers, the exponent tells you a lot. So look at, here's our H3O plus concentration. If that exponent is bigger than 10 to the -7, 10 to the -7 is like the cutoff point, right? That's our neutral pH. If your exponent is bigger than 10 to the -7, that means the acid is going to win out. If your H3O plus concentration has a value where its exponent is less than 10 to the -7, so in this case it's 10 to the -9, I know that I'm going to have more base than I'm acid, so it'll be a basic solution. Let's go the other way. Okay, I want you now to calculate the pH. I'm sorry, I want you to calculate the H3O plus concentration for the solution when the pH is 4.8. A lot of times I see students using the wrong equation in the wrong direction. So make sure you've got all that covered up for your little square. In this one, we want to use the other equation, which says that the H3O plus concentration is equal to 10 to the negative pH. I'll give you a minute for that. Okay, so this one, well, there's all the equations, okay, that I gave you in that square. There's the pH, different methods you can go through. We are going to, they did the inverse. So this is, I'm trying to figure out, they flipped the equation for us, but this is what we're doing here. So pH will equal 10 to the negative 4.80. When you plug that in, you should get 1.6 times 10 to the negative fifth molarity. Do one more down here. Here's a pH of 8.37. I want you to calculate the H3O plus concentration. It is literally the same thing that we just did, just a different number. Okay, so for the second one, we're just changing up the number that we're using. So the pH is 8.37. And it doesn't give it to us. That's okay. I'll calculate it out real quick. So it will be 10 to the negative 8.37. We get, it's a pretty small value. I get 4.27 times 10 to the negative 9th. Yes, no, maybe so. You've seen how those equations work. It's really just plug and chug. I think the most intimidating thing about it is people get freaked out with all the like really, really tiny exponents and stuff like that. But the equations themselves are pretty simple. So I'm going to give you a two-stepper. Here's our square. Let me shrink out a little bit. Not so far. All right, so let's say, what is the pH of a solution with OH concentration? I'm just going to type this out. This is a mess. Okay, so what is the pH of solution with an OH concentration of 3.6 times 10 to the negative 6? That little caret thing there is an exponent. Okay, so 3.6 times 10 to the negative 6. That's the OH concentration. So you're over here on the box. You need to come up with the pH. It's a two-step problem. So you can go two different routes. It's up to you which one you want to choose. I recommend going this way because this is really fast. But if you want to go this way, you can. Maybe 3 minutes for it. so for this one, we know the OH concentration, which is this here in the upper right-hand corner, and we need to get to pH. So you could use the Kw constant to go from OH to H3O plus and then from there to pH, but I don't like using this equation if I don't have to because this one is so much faster. So I'm gonna go this way. So I'm first gonna take my OH concentration and I'm gonna solve for POH. And so POH should equal the negative log of the OH concentration, which we have right here, which is 3.6 times 10 to the negative 6. And I end up with a POH concentration of 5.44. Now, the problem doesn't want POH, it wants pH. We don't use a POH a whole lot in chemistry or really in everyday life. Things are usually referenced in pH. So in order to get pH, well, pH plus POH has to equal 14. That's just the rule. So we can rearrange this real quick and go 14 minus POH will equal my pH. And so we just take it, subtract it from 14. And we end up getting a pH of 8.56. If you were to say, hey, is this acidic, basic, or neutral? Looking at that pH, I would say that this is basic. So on your test, since you guys have the luxury of having notes, I would just have this available. This is just a nifty way to have kind of all those calculations put into one place. It's a little bit left on the slides. Yeah, just talking about buffer solutions. So a buffer solution is a specific type of solution that contains a certain amount of a weak acid with its conjugate base. All right, so remember those acid-base pairs, conjugate acid-base pairs? This is a weak acid with its conjugate base. And what it does is it prevents the solution from changing pH. So your blood is a great example of a buffer solution. It keeps the pH of your blood between about 7.36 and 7.4. If your blood drops below 7 or gets higher than 7.8, which is a pretty narrow window, you can die. So because it contains both the weak acid, which we know doesn't fully dissociate, and its base, anytime I add base, the weak acid will neutralize it. Anytime I add acid, the weak base will neutralize it, and we get a resistance to pH change. So this is an example of a buffer solution. We've got this thing right here. This is a weak acid. When we move to the other side, here is the base. Here's its conjugate base. If I was to add acid to solution, like let's say we added HCl, the weak base that's present is going to eat it all up and neutralize it and produce the weak acid. Vice versa, if I was to add, let me go back for a second. If I was to add, instead of an acid, I was to add a base. This first one is adding a base. The base will be eaten up by the acid. So the acid consumes any added base and the base consumes any added acid to keep a pH that's relatively neutral. And this talks about acid rain, and we're not gonna worry about that. And that's it, okay? So that's the end of all of it. Oh my goodness, that's it. That's all the information you need in your head. So you just need to make sure you have all of that memorized and you'll do great on the final. I mean, this chapter plus the 14 before it. But there's no more new information, okay? So you will have a test, don't forget about the test. And then next week is sort of review week. So I don't want to say anything that isn't true, but yeah, okay, great. So your final exam for this class will be Sunday, Monday of not this weekend, but next weekend. And we will have final exam review all next week. So Monday we'll do the first 2 tests. So all the stuff that goes through Lewis dot structures. And then on Wednesday, we'll do the second half of the class with, I don't remember the exact chapters, but test 3 and test 4, which was kind of the more complicated stuff. So yeah, that's it. That's all we've got. So I've got some grades, labs to grade on my end, and you guys have one more lab to submit on your end. I did have somebody say something about not being able to access part of the lab. So I'll take a look at it and send you guys an email if I see anything. If you come up with something as well, if you're having issues with it, just send me an email and we'll try and get that squared away. Yeah, so that's all I've got for now. So hopefully I'll see you next week during review. Yeah, if I don't, have an awesome semester. Have an awesome summer. It's not the end, but it may be the last time that I talk to some of you guys. So, I will see you next time. Stay around if you have any individual questions or personal questions, and we can go over it.